to the right proportions. So that was the point there of solar neutrinos, that the sun is powered by the core, high pressures and temperatures with a dash of quantum tunneling. Hydrogen, those protons are able to overcome the repulsive force and join up, create helium, and E equals mc squared, energy gets released. So then we talked about stellar evolution. We introduced the Hertzsprung-Russell diagram. This is a nice big jumble of stars, and you might say, how do they know that that star is, you know, that one might be a red giant, this one's the main sequence? How do they know what evolution? They look at a star, analyse the light, and they'll tell you what evolutionary stage it's at. How do they know that? And they do it, they use this tool. So the HR diagram plots either a linear luminosity, how bright something is, against linear pressure, or linear luminosity against linear temperature, or in a logarithmic fashion, luminosity against pressure in a logarithmic fashion, or logarithmic luminosity against logarithmic temperature, or sorry, I was distracted by someone snoring in the back. I see people snoring, and I've even seen people snoring in the front seat. Seriously.
We'll sleep on it.
D. Yeah, D. Okay, who hasn't had a chocolate? Who said they genuinely knew it was D, and they haven't had a chocolate? Oh, yes. Who else hasn't had chocolate? Oh, down the back. Oh! Okay.
Sweet nothing.
So let's have a look at the Hertzsprung-Russell diagram. Three basic features are seen. It's luminosity versus temperature in logarithmic fashion. Stars are seen in concentrated groups, and from there you can determine what evolutionary stage of the star is. So that's your take-home message, but let's have a closer look. That's what it looks like. So the x-axis, you've got temperature here. It's in a logarithmic fashion, and the key is it's got hot temperatures over here, which can be up to 100,000 degrees Kelvin here, and it goes right down to about 1,000 degrees. So my point there is the temperatures go on the x line. It's in a logarithmic fashion, not linear. You've got your hot, most, you think you start with a small number, but it works such that it works better this way around. And the other key point is the range. You know, 100,000 up to 1,000 degrees Kelvin, that's the range. So stars really vary a lot in their range. The y-axis, going up here, you plot luminosity, once again in a logarithmic fashion. And of course the reason why mathematicians use logarithms is to try and fit, on graphs, is to try and fit a large range into some sort of sensible graph. So it's logarithmic. And look at the solar units. So it's going solar units. There's one solar unit, meaning the mass, the luminosity of our sun. And it goes right down to 10 to the minus 5. In other words, 0.0000001 solar mass, that's luminosity, so pretty dim. And it goes right up to 10 to the power of 8 luminosities. 6, sorry. So that's 1,000,000 times brighter than our sun versus almost 1,000,000 from the power. So a huge range of luminosity, and it goes from dim to bright. So that's called the Hertzsprung-Russell diagram. Now it leads to two main observations. First of all, there's a correlation, but also there are groups. This group here, it runs up here, that's called the main sequence. And that refers to when stars are burning hydrogen into helium in their cores. And by definition, that puts them on the main sequence. The bigger stars always burn through their hydrogen quicker, so they spend less time on the main sequence, and less stars here. And the other take-home message is stars spend 90% of their life on the main sequence. So 90% of their life they spend burning hydrogen to helium. Once it's all used up, they go through a series of stages called red giants and so on, and before they finally either go into white dwarfs or go supernova. But once again, your giants are all group, your supergiants are all group, your white dwarfs are all group. So it immediately puts things into groups just by doing this simple graph. So it makes sense. If you see a star, you measure its luminosity, you measure its temperature, it's going to end up in one of these groups, and that will tell you a lot about that star. It will tell you its stage and its evolution, which in turn tells you what processes are going on in its core, just by two measurements. How bright is it, and how hot is it? And it tells you what's going on in the different layers of the star. Sorry, Seth?
How can you, if you go back to your Jackson Pollock image at the beginning of the section,
Which one?
that one,
Yep.
how on earth do you accurately find information on, you know, anyone there in the background without getting information from one next door?
This is pretty much probably a wide angle view, probably at least scientific. I'd say this is not a very, I'm going to show you when we do the colour magnitude diagram, I'll show you an example of maybe focusing on a cluster. But yeah, good point. I think this is more of a pretty picture versus a scientific picture. But you're right, it's like globular clusters, which we're going to talk about shortly. Jeepers, how do you get in the way amongst that lot? You tend to take smaller field of views.
Right.
Yeah. But yeah, good question.
We use a technique here when we're doing research called crowded field photometry,
Yep, you go.
which is specifically to answer that question that you asked. And it's not simple.
Yeah. So you're with difficulty, I suppose, in the answer, isn't it?
Any choice.
So you can automatically tell what, for just those two measurements, and you, from there you can tell exactly what's going on inside the star.
Just before you go off that diagram, you mentioned, why do we plot things on log scales?
Yeah.
The key thing there is it shows power relationships. So
Yes.
rather than something that's a linear, like
Yeah.
multiplied by 2 or 3, it's a factor squared or cubed.
Yes, which is the laws of nature too, isn't it?
Yeah.
You drop you drop a big, say, a big ball bearing or something, a bearing onto the ground. I remember there was a documentary once. It was one of those drama ones. It was early science about a couple of years ago. So I've discovered it. And they've got a big ball, see, John, big ball bearing, sort of big, dropped it from a certain angle, and then got another one from double the height. And the little crater it made in the sand was 4 times as big, double the height, which came up with the R square bit. So the laws of nature often do go in powers. Yeah. Okay, so the colour magnitude diagram is used to study spiral elliptical galaxies, globular star clusters, open star clusters, globular and open star clusters. Well, sorry, I was texting it. Okay, who says it's up to E? And it's globular and open clusters. So the answer was D. So who hasn't been a chocolate and genuinely says, oh, it's D? So, oh, you got it? Oh, Kevin, take 2. Here you go. Oh, drop it.
Nice.
Who I did? Does anyone? Yeah, we're all good. Okay. Gosh, some of those people chocolate that come over here tonight and great lunch. Yeah, absolutely. They're used for studying globular and open star clusters. So we're going to talk about what is a colour magnitude diagram, how do you construct one, and then how do you interpret it. It's very similar in principle to the Hertzsprung-Russell diagram, so you remember that one there, with the temperature and the luminosity. But this time, instead of luminosity down the side, we talked about the formula luminosity equals the mass, the magnitude, the absolute magnitude. Remember, just stepping back, absolute magnitude refers to actually how bright the star is when you're 10 parsecs, so the set distance from the star. It's a more sort of absolute value, absolute magnitude, as opposed to the term apparent magnitude means how bright the star is from Earth, and so on. And I think I had this formula right. I think it was you, Chris, wasn't it, who called me up on the formula? I had to go home and correct it. I think our original slide had the formula wrong or something, but it was the absolute magnitude times 4 pi r squared, r being the radius of it. And I think actually it was Chris who pointed out that's the surface area of the star, of a cube, of a sphere. So it makes sense how the absolute magnitude or how bright something is all related there. So what they do is you know the luminosity of something, so you can work out its magnitude from there. So it makes sense. Hey, what's wrong with just putting magnitude instead of luminosity on here? The two correlate quite nicely. The other concept here is star clusters. You might say, well, we're measuring the absolute here, but should we be a bit more scientific than that? Guys, we've got the absolute magnitude. But when you get these star clusters, for all intents and purposes, they're roughly the same distance from us. all the stars. So suddenly you can substitute you can substitute the absolute magnitude with apparent magnitude. Because it doesn't matter, the distance between them doesn't matter because they're all roughly the same. So you measure how bright something is through your telescope, that's your apparent magnitude, you slap that up there, and that's a proxy when you're dealing with a star cluster for luminosity. Then, instead of temperature, you can use what we call a colour index, which reflects the temperature you've got on the X. Now, I know what you're thinking, you say, excuse me, what's a colour index? So let's talk about measuring colours and so on. When most of us look up at a telescope, which is a basic telescope, you measure the brightness and so on, you're measuring the brightness of all the different wavelengths combined. That's what we do, we look at our eyes and so on, and mixing it up. What astronomers will do is they will put what they call a filter wheel in front of your telescope. And there's various filters, all sorts of filter systems. There's a standard one, and for example, they might call it U, this is the UVBRI, and this is the effective wavelength. So these filters, you put a specific filter in front of the telescope, in front of its in front of where the light's coming through for your CCD camera. You're only interested in letting certain wavelengths come through. You know, the I one lets you close to infrared, red down the reading of the spectrum, visual, V for visual, because it's in the middle of the visual wavelengths of the yellows and the greens, B for blue and ultra, and U for ultraviolet. So these filter wheels are put in front, you flick the filter in front of your imager, and you're only interested in certain wavelengths, certain bands of wavelengths to come through, and you measure how bright they are in those specific wavelengths through those specific colours. So photometry refers to measuring the brightness of something, the magnitude. The colour index, all that means is the difference between any two different filter magnitudes. For example, the value you might measure something with a B filter on, and it comes to a certain magnitude, say 10. Then you go and slap your visual filter on, your B filter, for this wavelength, and you find, oh, okay, we've only got a magnitude of 8. So the colour magnitude of that star is 2. And this colour index is a lovely reflection of the temperature of the star. Just like colours, where you look at a flame, a hot flame is more whiter or blue than, say, a low lit flame and a lower temperature is more red. Same principle. So they use the colour index. So let's go back, and here's you can use difference between any two. Commonly, you tend to use B minus B, the most commonly published papers. You can see it's just the difference between the magnitude of two different colour filters. It's called the colour index, and that reflects temperature quite nicely. So that tells us a lot about open clusters. This is an open cluster. This is M67, an open cluster, which we're going to look at closer shortly. There's your 47 Tucanae, that's a globular cluster, really old stars, all densely packed in there, tightly gravitationally bound, and these are much less, there's probably 1 million or so stars in there. There might just be a few hundred of these stars, loosely gravitationally bound, or young stars. So let's have a closer look at constructing one. So M67. So first of all, you might put your, I think this is one with the M67 through a B filter. So here's all your stars. That's question 2, so that's just looking at part of the field here. This was part of one of my assignments, and I got to know every individual star patterns within patterns. You know, as a kid when you pick strawberries, if you close your eyes and all you see is strawberries. I closed my eyes every night for weeks when I was looking over this. All I saw were these star patterns. I think I knew them in my sleep, where every individual star sits. Of course, computers will do it these days. So that's through your B filter, where it might look through, and that's all calibrated and so on. And then you get the same star field, but this time this is what it looks through the R filter. And all those individual stars have slightly different, you pick a star there, it's a great one, HGI, click through it here, different brightness. Yep. So what you do then, on this side, remember we have to plot magnitudes. You just grab one. I just grab the R magnitude here. So it's a scatter plot. So each individual star, you just put somewhere in there. I think I just chose about 120 random stars in there, the easiest ones. And I found difficulty separating them. Now I'm not a astronomer, so I was just going in there with my basic software. I did have difficulty, but as Tony said there, it is a specialised field that we do it. So just plot the R magnitude here, how bright they move through the R filter. And then on this on the x-axis, just got the calculator or the Excel spreadsheet, we've got a value for the brightness of B, filter, minus the brightness in the R filter, put the values there and just plotted them all on a scatter plot. And there you have a colour magnitude diagram. But you might say, okay, that's nice, it's pretty, but where to from here? I'll interpret one. First of all, that's what they look like. Just once again, it looks like the Hertzsprung-Russell. It's a model. One, here's all your giants, supergiants, there's your main sequence. Right, also, if you plotted a whole big stack of them, that's what you get from the model colour magnitude. Very similar, isn't it, to the HR diagram? So what you do here is you identify the point on the main sequence where the stars are starting to turn off. So the main sequence would normally, in theory, be running up through here. So these stars here are all in the main sequence, still burning hydrogen and helium in their cores. But these stars are starting to turn off the main sequence. And now these stars here have used up all the hydrogen and they're starting to venture off into the red giant horizontal branch and so on, stages of stellar evolution. So that point there you identify is called the main sequence turn-off point. If you look at this graph, you'll see the value of R is 13.5. Works out to about here, 13.5. And the B minus R, the colour index, works out to about 1. That should be the main sequence turn-off. Okay, so that's the point that values the stars that are turning off and just use the last of the hydrogen. They're going to have an R value of 13.5, they're going to have a colour index of 1. You might think, okay, so what you do then is you can look up the charts in the literature through the stellar evolution theory, and you say, well, that point there is what they call a spectral class GO star that happens to have those values when it runs out of hydrogen. And in theory, its temperature should be 6,500 degrees Kelvin. Its luminosity should be 1.2 solar luminosity, its brightness. And I also know the mass should be about 1.2 solar masses. In other words, 1.2 times the mass of the sun. So once you know the mass of something, remember I said the bigger a star is, the faster it burns through the hydrogen. There's a definite correlation, a mathematical correlation between how big a star is its mass and how quickly it burns its hydrogen up. And this is the formula here. The main sequence time, the time that it spends burning hydrogen and helium before it burns all the hydrogen and pour up, is 10 to the power of 10 multiplied by the mass of the star in question, divided by the mass of the sun, all to the power of minus 2.5. That's the formula. So you plug all that in, a 1.2 solar mass star is approximately 4 billion years old. So immediately, what does that tell you? All you've done is done that scatter plot. You've looked at and identified your values for your main sequence turn-off, plugged in some simple mass, and you immediately know that that star cluster is 4 billion years old. And that's how they look at a star cluster and think, how do they know that that cluster of stars is 4 billion years old? How do they know how old a star is? That's how we tell. Colour magnitude diagram for a star cluster. Okay, so what else can they tell? So you've got these values here. So you've got the star that through your R filter, its apparent magnitude is 13.5. Once again, you go up and look in the literature for a spectral class, same class star. Stellar evolution tells you in theory its absolute magnitude through the R filter should be 4.29. So there's a difference in that we talked about during the year called the distance modulus. It makes sense if you know how bright something should be, but you know how bright it actually looks through here, you can calculate the distance between the two. So that's the formula there. Let's not get too bogged down by that. But the bottom line is the figure D for distance comes out to 857 parsecs, which is the distance in astronomy, and it comes to 2.8 thousand light years. Just through plotting a nice scatter plot, all the different stars with the colour index versus the magnitude in one of the filters. So you can immediately tell how far away a cluster of stars is, and you can tell how old that star cluster is, just by a simple colour magnitude diagram. So let's have a look at some. So there's Matariki or Pleiades, the open star cluster. It's young, so which means it hasn't had time for these stars here to use up all the hydrogen in their core. So it's just that main sequence turn-up point's nice and high. Go to a globular cluster, which is really old stars. So the stars have been around a lot longer. So all the stars that normally fit here, they've all left the main sequence, and there's the main sequence turn-up point there. So that immediately tells you that's an old star cluster. So if you had more more time for those lower mass stars to burn up the hydrogen. So let's just go back. So that's your typical young open star cluster colour magnitude diagram. This Pleiades, and that's 47 Tucana. So what you can tell just by doing a simple plot, simple observations and doing a plot. So, anyway, so a colour magnitude diagram, what does it tell you? Three things. The first two ones are easy. What does it tell you? To a star cluster.
Age.
Yes.
Systems.
Oh, gee. There you go. You guys sit in the front seat. There you go. Get a piece of chocolate. There you go. What else? A piece of chocolate. Fuel by sugar levels up, I reckon. Okay, so yeah, it's age and distance. What else does it allow you testing of? I haven't spoken about.
Stellar evolution.
Yeah, you've had some chocolate now. Bill's right. It tells you a lot about the test stellar evolution. Absolutely. So what you do is you match that up with your observed colour magnitude diagrams. You match the whole, get a whole set, many of them as possibly can, match them up with models of the theory and see if the two match up, and they match up beautifully. Stellar evolution, the theory of what goes on at what stages in the star's life, has been very, very successful, and this is the one way to test it with these simple colour magnitude diagrams.
JJ, sorry, I was just going to say, JJ at the University of Auckland is sort of big on that, particularly with massive stars modelling their evolution. What he's found is that early models didn't take account that a lot of stars are in binaries, and that does make quite a difference to the models when you include binary stars.
Yeah, and that's as Bill said, that story highlights as they keep refining it more and more and more. So JJ Eldridge, one of the astrophysicists at Auckland Uni, he's just like, well, hang on a minute, aren't most of our stars binary stars? Does that alter the way you look at observations? And it does. It's done all the computer work for it and updated, modernised the colour magnitude diagram to be more accurate. Okay, so we're up to large ground-based telescopes. Question 7. Which statements are true? Telescopes are the best at elevated locations, the best at remote locations. Mirror size is the most important specification. Size is a big advantage of ground-based space telescopes, but we need all of the above. You guys are going to be diabetes at this point. Don't come to me then. I know, you've already had one, Mark.
Oh, I've had two.
Have you had one? You did have one. Oh, yeah. Oh, hello. Nice to see you. All right. Oh, Tony. Okay. Yeah, absolutely. All of the above. Let's have a look at that. So these observatories, what have these three observatories got in common? That's the Keck telescopes in Mauna Kea and Hawaii. That there is the Silla Observatory, part of the European Southern Observatory Complex in the Atacama Desert. And that's also in the Atacama Desert, that's the element of the Atacama Large Kilometre Array. So the remote, why are they remote? Yeah, they're away from man-made electromagnetic spectrum of radio waves from microwave ovens and TVs and radio stations and of course light from city lights. Why are they elevated? I'm getting confused with saying what. Yeah, the point being that they're elevated, what I'll do is I'll give everyone a free for all chocolate. So they're elevated to high above the atmosphere, where the atmosphere is colder and it's thinner. Warm, thick atmospheres full of turbulence and distortion, full of the twinkling of the stars. So it's cooler, so the air is less likely to be moving around, it's a lot thinner, so you get less distortion and turbulence and so on. And the other reason it's up high, as we talked about, water vapour in the atmosphere absorbs infrared radiation. And if you get up above about 3,000 metres, which these guys all are, you're above 90% of the atmospheric water vapour, which means suddenly you've opened up, you can see 90% more light coming in from infrared wavelengths. Oh, I've got this right. Chocolate.
about absorption.
Okay, so the advantage of ground-based telescopes, it's all about size. When you go and buy a telescope from Andrew, you know, impressive, say how big is the primary diameter, primary aperture. Don't say what the magnification. It's all about size. So size allows you capturing more photons, more packets of light. So if you're measuring something, if something's more brighter, what does that allow the telescope to do?
See different things.
Yeah, so you don't see different things. Have you had a trumpet?
Only one.
Only one. You're lucky on this.
Wait, two.
Who else? Here you go, guys. Oh. Okay, so if you're picking up more photons, because your size is bigger, it's capturing more light, you get brighter images, and that allows you to see dimmer and fainter, further away objects. So it's a big plus. So also it allows greater resolution. So if you're seeing something in high resolution, what does that allow you to do? Somebody said it over there. Detail, yeah. I think it was these two gentlemen over there. Did you get a job? These two gentlemen, yeah. Yeah, it allows you to see more detail, absolutely. So suddenly you can see things further away, and suddenly you can see things in more detail. So the other thing is, yeah, you can serve new technology, take advantage of new technology upgrades. That's not really done, notwithstanding the Hubble telescope. 99% of all the space telescopes, once they're up there, you can't upgrade them, you can't service them, so on.
There is an issue with the key ones in particular, not so much with the key, but the location. There's the local Hawaiian Jupiter telescopes being on the mountain.
You do run it.
Yeah, and they're still trying to block the construction of the 30-metre telescope. But just recently, actually, they've got a building permit to put it in the Canary Islands as a backup. It's been approved by the Spanish government, so they're obviously still heading in the balances to whether it's going to go ahead or not.
Yeah, so that's been a big problem in Hawaii with one here that telescope. Beautiful site for observing, but yet the locals, the native Hawaiians, are very much against it in terms of spiritually soiling their lovely mountain and so on. So that is a very real problem. But now here's an example of technology of adaptive optics that counter turbulence. So this is on the Keck telescope. They shine laser light. They excite sodium atoms about 90 kilometres in the atmosphere. They know how it should be responding in twinkling. They measure the amount of twinkling. So they can calculate the turbulence, and they alter the mirrors, the shape of the mirrors, to counter the amount of turbulence, to get rid of the turbulence in their images. Now, who can give me an idea of the figures of how many times per second is those 10-metre telescopes? Sort of almost the size of this room. And these telescopes are just microscopically adjusting themselves. 200.
About 2,000?
2,000 times per second. These telescopes, sorry guys. So these telescopes are adjusting themselves 2,000 times per second, just making small adjustments. Who can tell me roughly by how much they're actually adjusting themselves 2,000 times a second to count the turbulence?
I need that.
Lara, is there one of these? Have you had one? Yeah. I'm just going to say, you guys on the back? Oh, George, there you go. Come in, here you go, George. Now, Ben, is it Ben? There you go, Ben. Okay, so, yeah, it's 4 nanometers. These 10-metre mirrors, the computers and obviously are analysing the signal coming back from these laser lights with a feedback system to the mirrors. And the mirrors, the actuators in the mirrors, adjusting the mirrors by an accuracy of 4 nanometers, 2,000 times a second. That's the technology involved in the book. It all came out about the late 80s, whereby the images from the Keck telescope are superior in a lot of circumstances to the Hubble. So, question 8, observing space telescopes. Hubble, of course. Which statements are true? Space telescopes detect light in a broad wavelength range. They don't suffer from atmospheric distortion. They're restricted, however, by cost and how big the mirror can get. And they cannot be really maintained and upgraded, or all of the above. Who hasn't had a chocolate at all? Why don't I be off? Is that all you can have?
Yeah, over here.
Oh, okay. Does everybody else have one?
Yeah,
Eric, the cameraman.
Yeah, that's Steve.
Lead one, take one.
Yes.
Perfect. Catch. Okay, excellent. All of those points. Let's just go over them. So, as we talked about, the atmosphere absorbs most of the range of wavelengths of light. Light comes to us from astronomical processes, stars and supernova explosions, high energy gamma rays, X-rays, ultraviolet, visual, infrared, and then your microwave and your radio. And you can see here all of the gamma rays, the X-rays, and ultraviolet essentially get absorbed by the molecules within the atmosphere. The visual light is a very narrow bit, between about 400 and 700 nanometers. That gets through to us. Look at the infrared, pretty catchy, isn't it? Most of it doesn't get through to us. There's just a window here that, of course, our radio telescopes pick up on. So you can see most of the range of wavelengths from astronomical processes coming to us from the rest of the universe is all blocked by our atmosphere. So we get telescopes above the atmosphere, so you don't have to worry about it. Don't have any distortion or turbulence, and you've opened up a window to all these different wavelengths of light. So here's covering the full spectrum. We all know that one, Hubble. Who can tell me what telescope that is? Chandra. And what range of X-rays? That one. That's the Fermi telescope, the gamma rays. How about this one here? That's the Spitzer for infrared. This one's the Galex for ultraviolet. We all know this one. So it's just the Hubble. Yeah, when was the Hubble launched and how was it launched? Yeah. 1995 space shuttle, absolutely. And this is just one, just to relax when our time's almost up. So I've just gone here for the big screen. Let's enjoy a bit of the visual. That's it being released from the shuttle bay. That's an artist's impression of what that would look like. That's a photograph from the shuttle. Beautiful piece of equipment, isn't it? That's them servicing it, and that's what I said, notwithstanding the Hubble, that's one of the very few telescopes that can be serviced. That's them replacing the wide field camera 2 with the wide field 3, that was the Mark 3 of the camera. That's a pretty cool shot.
What was wrong with the mirror?
It was, the primary mirror was out there, only talking sort of, it's just a fraction out. The essentially was short-sighted. They made 2 of them, and the one that stayed behind turned out to be perfect. So they had to put what they call co-star up there. They took some instruments out and put a sort of lenses in its place, essentially a pair of dark glasses, which corrected for it. Yeah. And the funny thing is, you should raise that. The press just honed in, it's like a white sheet with a black spot on it. They just honed in on it, something negative. A lot of people out there mention the Hubble and go, oh, wasn't that just a big whatever, total disaster? Yeah, no, that was probably arguably one of the most successful scientific instruments ever produced. So, that's an interesting raise that. But yeah, they overcame that with the co-star. Like a pair of glasses essentially over the top of the lens. And that's the final mission to service it. And that's it when it's finally released it. That's the last anyone saw it directly with their own eyes. So the quiz summary, crater numbers, sizes, density, and numbers are used to date surfaces. It's correlated by the radiometric measurements from the moon rocks. lunar rover was on the last 3 missions. Hugely impressive amount of field geology they were hamstrung how far they could go by how much oxygen the astronauts would have in their backpack should it break down and they had to walk home. Star temperatures are measured by spectroscopy, splitting different wavelengths. Plotting on a black bodies type graph, looking at the peak and also looking at the energy levels of the different elements. It's got a bit funny, isn't it? You could just put Sun is powered by nuclear fusion. The protons, positively charged, are able to overcome that repulsion by temperatures of 15 million degrees in the core of the Sun. Quantum physics said that quantum tunneling should go on, which should allow a small number to happen, and indeed that is what's happening, which finally enables it to occur. Crazy, isn't it?
What?
It's all good fun. Someone's had too much chocolate. Hertzsprung-Russell diagram plots the luminosity on the y-axis, how bright something is, versus the temperature on the x-axis, and it's a logarithmic fashion, and it covers a huge range of each field. Okay, colour magnitude diagram, very similar, and it's used to study star clusters. You're plotting to do with colour index versus the actual magnitude in a colour vector. And you can tell the distance to a star cluster, you can tell how old it is, and it's a lovely way, like a stellar laboratory, if you will, to measure how good our models are of stellar evolution. What was I on this night?
No idea.
It must have been single motion. Either that or one of the cats today. I'm going to think about whenever a cat walks into the bath, it's one of those touch screens. You touch it and things happen. So you know what cats like smooching and big bushy tail. As soon as the cat walks in the room, hit the save button. I suspect the cat's probably responsible for this. Ground-based telescopes are remote, away from man-made pollution of light and so on. They're elevated to get above the atmosphere, so they get less turbulence, and also above most of the water vapour. Size is so important, that's really the key step. And space telescopes cover pretty much a much larger range of wavelengths, that's the big plus, but they're hamstrung by it. They can only be so big because it's expensive putting them in space. So you know, when a rocket sits on the launch pad, send a payload into space, 85% of the mass of that rocket standing on the pad is fuel to get the payload into orbit. That's how inefficient the whole process is. So that's why space telescopes are not large. And the Hubble's pretty clear at 2.4 metres. So I hope you've enjoyed it. It's the end until next year, and drive home safely and have fun and have a great Christmas. Look after one another. Thank you. I think we've covered all the questions as we go. Anything else? I'm all good. Oh, I was I really under the cat. I've got a whole stash of them at home, so I'm just going to pick it up.